week 11 live interaction section. So in week 11 lecture videos, we have mostly discussed about grid generation methods as well as finite volume formulation uh, in CFD. So let's move on to questions. First question: for the solutions of Navier-Stokes equation in irregular geometries, which of the following grids can be used? Options are first one Cartesian grids, second one unstructured grids, third one second one structured grids, third one unstructured grids. Options are both 1 and 2, option B both 2 and 3, option C all the above, option D only third one. You can inbox your answers. Yes, the answer is right. We can use both structured as well as unstructured grids for Navier-Stokes equation for irregular geometries. So option B is the right answer. Moving on to the next question. Which of the following can be claimed as an advantage of unstructured grid over the solution of structured grid? Statements are: first one, ease of grid generation. Second statement, ease of grid refinement. First one is grid generation, second one is refinement. Third one is ease of solution of discretized equation. So third one is ease of solution. So which of these are the advantages of unstructured grid over structured grid? Our options are 1 and 2, option B 2 and 3, options C 1, 2 and 3, option D only third one. You can inbox your answers. So the three statements were ease of grid generation, ease of grid refinement, ease of solution. So we have gone through the videos. Unstructured grid by ease of generation as such, we can't say, but it's true to an extent that like for irregular geometries, the grid generation will be difficult. But For other geometries, the unstructured grid can be easily generated, and also it can easily refined. But ease of solution won't be there, because even for a rectangle geometry, if I am using some triangulation discretization for 2D, for a 2D element, the mostly is triangular elements. So if we are using some triangular elements for discretizing a geometry, for solving our algebraic equation, we will be needing some distances, some intercellular distances, and the geometric properties from the mesh or the cells are being taken into our system of equations. So these conversion, when the elements are not structured, if it is triangles, the quadrilaterals, or such elements are there, then the calculation of this centroid to centroid distance, or uh, obtaining the geometrical properties for each cell for a unstructured grid will be difficult, and thereby that can complicate the uh, solving process. So ease of solution won't be there for uh, unstructured grids, but to an extent grid generation is uh, easy. Also, grid refinement is also is once a coarse grid is generated, constructed coarse grid is generated, then a refinement is also easily can be easily done. But ease of solution won't be there, because, as I have mentioned, uh, for unstructured elements, triangles or quadrilaterals, our when our domain is meshed with quadrilaterals or something, then uh, the calculation of angles as well as the distances or the geometric properties for each particular volumes or cells will be difficult. That will make the solution process more tedious. So our answer is option A, that is first two statements stands for unstructured grids, whereas third one is uh, mostly an advantage of structured grid, ease of solution. Moving on to next question. Which of the following statements is not true when we use structured grid for flow through a complex geometry? So the question is about finding a false statement regarding use of structured grid for a complex geometry. The statements are: body fitted grids can be used only on two-dimensional geometries. Second statement: the finite difference techniques cannot be used. Third statement: the diagonal dominance condition of the coefficient matrix is preserved. So these are the three statements. Our options are: only third statement is false. Option B: both 1 and 2 statements are false. Option C: both second and third statements are false. Option D: all of the statements are not true. You can inbox your answers. Let's check the statements. First statement is body fitted grids can be used only on two-dimensional geometries. That is a wrong statement. We can use body fitted grids on three-dimensional geometries as well. And second one is finite difference techniques cannot be used. It is not likely that finite difference methods can be used in any condition, but the issue is with uh, the ease of generating things, ease of generating structured grids on for that will match for finite difference techniques. So finite difference method can be used. So again, this is also a false statement. So 1 and 2, both of them are false statement. Again, the third statement is diagonal dominance condition of the Gaussian matrix is preserved. So it is not preserved when we use uh, body fitted grids. Uh, Initial generation of the Gaussian matrix itself may not be a diagonally dominant. We may not be we maybe have to do some preconditioning methods, something called preconditioning that we have discussed in last week. Preconditioning to make it diagonally dominant. So all of the statements are false. Then our option is option D, that statements 1, 2, and 3 are false. Moving on to next question. Which of the following statement is true about the transformation of the Laplace equation into a non-orthogonal curvilinear coordinate system? So the question is about transformation of Laplace equation into a non-orthogonal curvilinear coordinate system. Options are: the elliptic equation remains elliptic, the elliptic equation becomes parabolic. Option C, the elliptic equation becomes hyperbolic. Option D, the parabolic equation remains parabolic. You can inbox your answers. So, if you remember, Laplace equation is a elliptic equation. So, you can simply cross out the last option. Then remains are three. Elliptic equation remains elliptic, remains because parabolic or hyperbolic. Again, uh, Laplace equation is if you are taking in two dimension, then uxx plus uyy is equal to 0. This, even if you are transforming it into a curvilinear coordinate system, then this there won't be any additional terms, or there won't be any first order terms uh, coming to the equation. So it will remain elliptic. Our option A is the right answer. Next question. Which of the following statement is true about ADI scheme, that is alternating direction implicit scheme? Statements are: it is an iterative method. Second statement, it requires diagonal dominance for convergence. Option 3, sorry, third statement, it can be applied to three-dimensional problems. So these are the three statements, out of which the question is to find true statements regarding ADI scheme. Our options are first and second statements. Option B, second and third statements. Option C, first and third statement. Option D, all the three statements. You can inbox your answers. Yes, regarding ADI scheme, alternating direction implicit scheme is an implicit scheme where we will be splitting our time step. The time step t plus 1 is splitted into t plus half each. So in first half we will be moving in one direction. So I am considering one linear section only, not two-dimensional or three-dimensional, just explaining the concept. So the time step is split into half, and it will be the spatially it will cover alternating direction. In first half of the time step or first fraction of the time step, it will be uh, moving to one direction, and in next half it will be moving in another direction, sweeping in another direction. So our statements are: it is an iterative method. It is true, it is an iterative method. Again, all the methods need diagonal dominance for convergence. So second statement again true. It can be applied for three-dimensional problems. Yes, it can be applied for three-dimensional problems. This is a scheme, not any meshing method or something. So this is a scheme. So schemes doesn't have any bias in between three-dimensional or two-dimensional problems, unless for our scheme function OTC method. That's again not a scheme. So here all the three statements are true. So our option becomes option D. That is statements 1, 2, and 3. Moving on to next question. For the solution of Ax is equal to B, which of the following decomposition of a matrix is the most implicit? So the question is about which of the following decomposition is most implicit. That is, most implicit mean it will be having most number of terms in the current iteration steps. Options are LU decomposition, option B incomplete LU decomposition, option C LU plus N as in SIP, sorry, statement. So out of three statement you can choose. Yes, you are right. Option A, LU decomposition method is the most implicit method where A is split into L and U, one lower triangular method, lower triangular uh, matrix, and other upper triangle method. Here, uh, in this, the number of elements in both L and U has to be solved. There, the number of elements, non-zero elements will be uh, greater, whereas in incomplete LU method, the number of non-zero elements are reduced. So our option is first option A, that is LU decomposition. Moving on to next question. The advanced iterative techniques are used primarily to enhance which of the following aspects of basic iterative methods? So the question is about why we need advanced iterative methods over basic iterative methods. Options are uh, convergence condition, to improve convergence condition. Second one, to improve convergence rate. Third one, ease of computation. So which of these aspects are enhanced in advanced iterative techniques? Option A, 1 and 2. Option B, 2 and 3. Option C, 1 and 3. Option D, 1, 2 and 3. You can inbox your answers. So actually, if you have gone through the videos, why we need advanced iterative methods. So why we are iterating the solution, why we are iterating the system of equations. So we are iterating the system of equation. Iterating is to improve accuracy. Accuracy will be achieved if and only if the convergence is met. So our primary target is to improve the accuracy by improving the convergence. So that's why we need advanced iterative techniques. But uh, a lot of methods that we are depending for advanced iterative techniques, that is preconditioning, uh, and also some techniques use a lot of guesswork and some pseudo time loops. All such things will increase the computational process. So our primary target is to enhance the accuracy by improving the convergence. So This first and second aspects are improved, while the use of computation or the computational cost is something what we have to compromise. So option A is our answer, that is 1 and 2. Moving on to next question. Which of the following statement is true about multigrid method for solving Ax is equal to B? Statements are: it uses multiple grids for the same domain. Second statement: it uses multiple grids for the same equation. Third statement: it solves the same equation on all grids. Options are first and second statement, option B second and third, option C first and third, option D first, second and third. We can look for answers. So in multi-grid method, we'll be using different set of grids for the same domain. So there will be fine meshes, there will be finer meshes, because extra course, and there will be a set of different levels of meshes depending on the geometry or the domain in hand. So what we do is when we are solving in a finer mesh, uh, if that particular set of equation is not being uh, getting solved, or some error is getting propagated in the finer mesh, then what we will be do is we will be switching it back to, or the multigrid method will be switching it into lower or coarser meshes, where the equations are altered, or some modeling will be done for the equations to uh, capture or to overcome the error, propagating error, and which is then smoothened and uh, fed back to the finer meshes. So this is the process happening in multi-grid method. So the statement, uh, first statement is true, again second statement is true, but it solves on the equation on same equation on the all grid. It is not true, because when it is moving, switching from one level to next level, the equations are modeled or modified uh, in order to capture the error or smoothen it, uh, to switch it back to that particular level of refinement. So option A, that is statement 1 and 2 is true, is our answer. Next question. In Delaunay triangulation method, the unstructured mesh generation is focused on which of the following? Options are creating elements with good aspect ratio. Option B, minimizing the total number of elements. Option C, maximizing the volume of each element. Option D, guaranteeing the conformity with the computational domain boundary. So Delaunay triangulation method is the most used method for unstructured grid generation. So what is the principle behind Delaunay triangulation method? Is our question. You can inbox your answers. Yes, you are right. Option A, that is creating elements with good aspect ratio, is what Delaunay triangulation method focuses on. Because a triangle is the lowest uh, shape or simplest shape which can divide area. When it when we are moving into higher number of edges, that is quadrilaterals or pentagons, the maintenance of good aspect ratio become difficult. So in Delaunay triangulation, or why we choose triangles, is that we can uh, focus on creating triangles with good aspect ratio. When the aspect ratio is different for different types of elements. If uh, any side or any geometrical proportion is way too skewed, then it creates hurdles for the computational process. So a good aspect ratio is one of the required qualities for a mesh, and Delaunay triangulation method ensures is um, created such that it will be refining the mesh for good aspect ratios. Moving on to next question. The advancing front method used for mesh generation is particularly useful for. So the question is on application of advancing front method. Options are simple rectangle geometries. Option B, complex geometries with intricate boundaries. Option C, uniformly spaced grids throughout the domain. Option D, refinement of existing structured meshes. Yes, you are right. Uh, Advancing front method can effectively handle complex geometries with intricate boundaries because it is advancing front. The term itself denotes that it uh, transforms or adjusts elements that will conform to the boundary. So it will keep on adding elements or keep on dividing the elements uh, until and unless it is fully conformed with the complex boundaries. So uh, such advancing front methods is well suited for complex boundaries or complex geometries. Moving on to next question. Octree-based methods for mesh generation are well suited for, again the question is on octree-based methods. Octree-based methods of for mesh generation are well suited for which of the following? Option A, generating highly anisotropic meshes. Option B, adapting the mesh based on the solution gradients. Option C, creating very fine meshes around small features. Option D, all of the above. Tree-based methods are mostly used for 3D generation, 3D mesh generation. Yes, you're right. All of the above. That is, octree-based measures can easily define into anisotropic measures. It can refine. It can provide refinement near small features, and it allows overall flexibility. So, octree method is based for, as I said, 3D measures mostly. Uh, the basic structural unit is a cube. Octree is, as you can spell it, it's octree, that is 8 and a tree structure. So if you have a structure, then it divides it into 8 octants. So first we have chosen a domain to a, if it fits it in the cubical space, then it divides into 8 uh, smaller cubes or varying size or section. Then this volume is again splitted. All each element is splitted. That such a tree-based uh, volume splitting is happening in octree method. So which this will uh, allow the user to define anisotropic measures as well as refinement and overall flexibility. Moving on to next question. A key advantage of unstructured meshes compared to structured meshes in CFD is option A, they are always computationally more efficient. Option B, they can accurately represent complex geometries. Option C, they require less user input for mesh generation. Option D, they are inherently more accurate for all CFD problems. You can inbox your answers. So the question is about key advantages. That is the most important advantage of unstructured mesh over structured mesh in CFD problems. Our question is on key advantage of the unstructured meshes, not just advantage. So if you see why we need unstructured meshes at all, so why can't we go with structured mesh? So the main requirement of an unstructured mesh is uh, required when the geometry or our computational domain is complex. So the main requirement of the unstructured mesh arises only when the geometry is complex. So even with that in our mind, if you approach the options, then we have only one option with complex geometries. Then again we can uh, confirm with other options also, that the first option is says that they are always computationally more efficient. That is not true. You know that we have discussed in the previous questions that solving procedure, the solution for uh, unstructured meshes are difficult as The obtaining the geometrical values from the constructed mesh itself is a tedious process which will add to the computational cost. So it is not efficient, computationally efficient. Then it requires less user input for mesh generation. Yes, comparatively, uh, it depends. For a complex geometry, the unstructured meshes will require less user input. So this is a advantage in the primary uh, outlook. But the question is on key advantage. And the fourth option says it is inherently more accurate to all CFD problems. So the all here makes it it is accurate, but it can be accurate, but it is not accurate for all CFD problems. So option D is also false. So only option that stands is option B, that they can accurately represent complex geometries. Because when our complex geometries will be having irregular boundaries, so unstructured meshes can capture and conform with the irregular boundaries. That's why we go for unstructured meshes. If our geometry is simple enough, then we can uh, create structured meshes with lesser user inputs. Moving on to next question. When choosing an unstructured mesh generation method for CFD simulation, a crucial factor is to consider. Options are option A, the total number of elements in the mesh. Option B, compatibility with the chosen turbulence model. Option C, the level of automation offered by the meshing software. Option D, the ability to capture the expected flow features. So the question is about what should be our main objective when we choose an unstructured mesh for our CFD simulation. So again, here the question is on unstructured mesh. So first you check anything there is on complex geometry, irregular boundary or something. There is nothing related to that on our options. Then the total number of elements in the mesh, the total number of elements in the mesh will be uh, more in an unstructured uh, mesh. And again, uh, we will be optimizing the number of elements in the mesh in any of the meshes. If it is unstructured mesh or a structured mesh, we will only try to optimize the number of meshes. Then compatibility with the chosen turbulence model. So that is have nothing to do with unstructured mesh. The level of automation offered by meshing software. So who said anything about meshing software? We can code it. In every software runs on some basic code. We can also manually code for unstructured mesh generation. So that's again not a factor. Uh, so for any mesh, not just unstructured mesh, for any mesh, our what we need is to first is to confirm with our geometry. The mesh is what dividing our computational domain into smaller domains. So first quality of the mesh is to confirm with the physical boundaries of our domain or geometry. Then next need or the refinement process or the mesh refinement process. That's a second step of our mesh generation. That is done to capture the expected flow features, not just unstructured mesh. It is happen for structured mesh also. So our mesh refinement or uh, mesh improvisation uh, is done for capture the expected flow features. Though this is our answer. Option D is our answer. Moving to next question. Which of the following statement about mesh quality is generally true for unstructured meshes in CFD? Option A, they always have better quality compared to structured meshes. Option B, they require more effort to ensure good element quality. Option C, they are inherently less accurate due to irregular element shapes. Option D, special care is not needed for mesh quality with unstructured grids. So the question is about which is a general fact or generally true for unstructured meshes in CFD. You can inbox your answers. Yes, you are true. You are right. Option B is our answer. If you go through the options, first option is they have always better quality compared to structured meshes. It's not true. And option C says they are inherently less accurate to irregular element shapes. But we are, it's not a general fact. But if we are improvising the element quality, we can get uh, accurate results compared even from the unstructured meshes. So it needs special care. So only option that is true is option B. So element quality has different matrices. We have discussed that in fourth, fifth week's session. It, the aspect ratio, skewness, uh, uh, smoothness, all those things uh, should be within some range, or the value should be optimized for us to get a better results, or for the better capturing of the physical phenomena. Next question. A common challenge associated with unstructured mesh adaptation in CFD is option A, maintaining good element quality after refinement. Option B, reducing the overall computational cost of the simulation. Option C, ensuring compatibility with the chosen flow solver. Option D, imposing complex boundary condition on the adapted mesh. The question is like the key challenge or the most important limitation of unstructured mesh. Um, if you go through the options, uh, the option B is reducing the overall computational cost of the simulation. So if it was there not this term, option B was our answer. But this only the question is about common challenge of unstructured mesh adaptation. So overall computational cost not just depends on mesh creation, it depends on the other solving scheme and a lot of other factors. So reducing overall computational cost is not our common challenge, but uh, our need, our primary need from a simulation is to get good results. So the next target is to achieve good results with less computational cost. So for getting good results, what we will be doing is to uh, refine our mesh, or refine our computational domain such that uh, the mesh will capture all the required uh, physical flow phenomenon to our required accuracy. That the term should be remembered, that required accuracy. We can uh, choose to which accuracy we need our results. So the computational methods and the mesh as well as the methods should ensure it is giving a required accuracy. So from if you uh, go through all these options, only two things are directly related to the measures, option A and option D. Again, uh, from these two, option A is the most important challenge because we know that we will be refining our meshes in successive cycles, but with unstructured mesh, we know uh, the element will be splitted uh, with some crude or limited input. Suppose we are giving minimum element size or something, not size or something, the element will be, we are, we will be reducing the side length of the particular cell or something. While doing that, it is a high chance that in unstructured meshes, highly skewed or highly uh, poor quality elements will be generated during the refinement compared to that of structured mesh. So, maintaining good element quality in unstructured grid is uh, the primary task related to unstructured mesh adaptation in CFD. The second option was true if the term overall was not there. Moving on to the next question. In structured mesh generation, in unstructured mesh generation, the process of assigning material properties to each element is referred to as option A, mesh refinement, option B, boundary condition assignment, option C, meshing convergence, option D, cell tagging. Comparatively simpler question. The process of assigning material properties to a cell or element is referred to as which of the following? You can endorse your answers. Yes, option D, cell tagging. So we are, it's a simple options. Mesh refinement, we know that it is successive refinement of the mesh to get an optimum mesh. Boundary condition assignment is assignment of assigning or boundary conditions to the mesh. Meshing convergence is like simulation convergence to uh, construct a mesh for a given set of criteria. And cell tagging is the process of assigning material properties. In case of our flow processes, it will be pressure and temperature. If it is a finite element process or something, and the elasticity and percentage, all such properties of that particular region should be assigned to that particular cell or each cell of the mesh. So such process is called cell tagging. Next question. In the advancing front method for mesh generation, how does the front progresses through the geometry? Options are randomly selecting points within the domain. Option B, iteratively adding points to the boundary and advancing inwards. Option C, dividing the domain into predefined subregions. Option D, sweeping a structured mesh across the geometry. So the concepts we have already discussed in the previous question. The question is on the method of how the front progresses in the advancing front method. Yes, you are right. Option B is our answer. Iteratively adding points to the boundary and advancing inwards. So these are different types of methods. Randomly selecting points within the domain is something like a Delaunay method or triangulation methods. Some of the primitive triangulation methods will be selecting points, randomly selecting points within the domain and then starts triangulating. But whereas in advancing front method, if we have a uh, domain, then first the boundary is uh, uh, boundaries are meshed or divided into uh, uh, divided into certain regions or small portions by iteratively adding points in boundaries. Then this is then related or connected together to form the shapes inside, which is then advances inside from the boundaries. So such a method is followed in advancing uh, front method, whereas the method like octree method, even though it is in three dimension, the octree method follows the third uh, statement, that is dividing the domain into predefined subregions. That is in octree methods, the all region is almost fitted in a cubical shape. Then it is then divided to smaller cubes of different aspect ratios. And sweeping a structured mesh across the geometry is the most basic meshing method when we do it manually or something. If we have a rectangular region, then we can interpolate the length or divide it into some particular element x. Then it will be swept from in some of the direction. In one direction, it will be sweeping the geometry, creating meshes in that direction. So all these are different methods to create meshes, but for advancing from geometry, option B is the right answer. Next question. The primary advantage of a body fitted grid in CFD compared to a Cartesian grid for complex geometry is option A, reduced computational cost, option B, improved accuracy near boundaries, option C, simpler implementation of boundary condition, option D, easier mesh generation process. So the question is advantage of body fitted grid over Cartesian grid for complex geometries. Yes, you are right. Option B is our answer. The question is, it is intuitive that the question is on body fitted grid. So why we need body fitted grid? We need body fitted grid so as to capture or conform our grid to the irregular boundaries. So that we need for improved accuracies near the boundaries. So there will be some flow phenomena having much importance at the boundary regions. So such regions require uh, more accuracy, and body fitted grid ensures that compared to a Cartesian grid. So we know the computational cost is more for body fitted grids, and also implementation of boundary condition again is not easy, and mesh generation process is also tedious compared to Cartesian grid. So only one primary advantage for body fitted grid is to achieve improved accuracy near boundaries. Near boundaries, our flow gradients will be high. To capture these uh, high gradients of flow, we need uh, improved accuracies near the boundaries. Next question. A well-designed body-fitted grid should have minimal skewness in its cells. What is the negative consequence of highly skewed cells? Options are increased computational efficiency. Option B, improved flow visualization. Option C, reduced accuracy of flow solutions. Option D, easier post-processing of the results. A simple question. You can unbox the answers. The question is so simple. Please answer. Option C is our answer. So the key is in the question itself. It's saying that minimal skewness is needed and if it is highly skewed, so it should only create adverse and negative consequence. So all the options other than C is giving some good results or good consequence. That is increased efficiency, improved for visualization, easier. So these are positives. Only the negative consequence is option C. That is reduced accuracy of flow solutions. So this is my question. And it is not just for our body fitted grids, any grids or any meshes. If the skewness is high, then it can introduce numerical errors that will in turn uh, affect the convergence as well as the accuracy of, uh, the accuracy of the solutions. Next question. Chimera grids are a type of body fitted grid used for option A, simple geometries with smooth curves. Option B, overlapping or intersecting objects. Option C, highly viscous flows with large velocity gradients. Option D, turbulent flows with complex vortex structures. The question is on a typical variety of body fitted grid, that is Chimera grid. You can inbox your answers. If you remember our third week's interaction section, we have already discussed about Chimera grids. Chimera grids is an example for overset meshes. So if you remember that much, then it was easy for answering the question. So just find this oversetting in the options. So option B is our answer. That is overlapping or intersecting objects. So in overset, uh, in Chimera meshes, what happens is that when we have the intersections, in basically what Chimera mesh is, that we have a broader mesh. In that, we can choose one particular portion to have finer things. So here this is mesh A and mesh B. So it's an oversetting kind of mesh. So this oversetting kind of mesh is mostly required when there is intersecting objects or other ways to reduce the computational complexity. So, so our option is overlapping or intersecting objects. For simple geometries with smooth curves, we don't need Chimera meshes. I think in our third week session, I have shown all the different types of meshes and what's an overset mesh. So Chimera mesh is a classic name for overset mesh, one variety of overset mesh. That's which is also a body fitted mesh. Next question. When generating a body fitted grid, a clustering technique is often employed. Two options are randomly distribute cell throughout the domain. Option B, increase the density of cells in regions of high flow interest. Option C, reduce the overall number of cells in the mesh. Option D, simplify the grid generation process. You can inbox your answers. Yes, you are right. Option B is our answer. That is to increase the density of cells in the regions of high flow interest. So it is intuitive from the question itself. It's a clustering technique. So clustering means we are increasing the number in one particular region. So from that itself, you can answer the question. So in body fitted grids, clustering technique is the method by which we will be adding uh, or we will be increasing the numbers of cells in particular regions of our interest to capture the finer details of the complex flow phenomena. Next question. Compared to the structured body fitted grids, unstructured body fitted grids are generally, options are more efficient for complex geometries. Option B, easier to generate automatically. Option C, more accurate for higher order numerical schemes. Option D, less prone to numerical errors. So it's a comparison between structured and unstructured body fitted grids. You can inbox your answers. Yes, again simple question. Option A is our answer. More efficient for complex geometries. Unstructured grids can easily conform to the intricate boundary shapes of our complex geometry, which will make it more efficient for complex geometries. Next question, again on body fitted grids. The major challenge associated with body fitted grid is option A, high computational cost due to complex grid generation. Option B, difficulty in implementing turbulence models. Option C, inability to handle moving boundaries. Option D, limited applicability in inviscid flows. You can inbox your answers. Yes, you are right. High computational cost due to complex grid generation. So when we need to create refined unstructured body fitted grids, then the computational cost or the meshing cost itself will become uh, high compared to other meshes. Next question. Mesh adaptation is a technique used with both structured and unstructured grids. What is the main purpose of mesh adaptation? Options are reduce overall mesh size for faster simulations. Option B, improve accuracy in areas with changing flow features. Option C, ensure all elements to have same aspect ratio. Option D, simplify post-processing of CFD results. So mesh adaptation involves both refinement or coarsening. It's not just refinement of the mesh. Mesh adaptation uh, includes refinement as well as coarsening. So what's the purpose of mesh adaptation? You can inbox your answers. So you are right. Option B, that is to improve the accuracies in areas with changing flow features. So in a in our computational domain or geometry, there will be areas or regions where the flow features will be different. So for such cases, we can use mesh adaptation. So when we, for example, suppose for some regions, if we have some, if you feel like something like this, so uh, we believe that this portion has more uh, flow gradients compared to other two regions. So I am naming it A, B, and C. So we feel like this B has some more flow features or flow gradients happening compared to other regions. Then we can refine this region B with respect to A and C to capture these things. As again, when comparing A and C, if we believe that we are uh, concerned more concerned in the results more in C region rather than A, then we can comparatively have a coarser mesh in A compared to C. So that selective refinement and coarsening is what is called mesh adaptation. So this mesh adaptation is done for two things. One is to improve the accuracy as well as reduce the computational cost. So when for some the machine, suppose the region A is larger compared to others, and we are not in particular a requirement of the flow details in A, then we can use coarser mesh, which will reduce the computational cost. But the results from the option A will be required to compute or solve in B and C. So in such a condition, we can go for coarser mesh in A and corresponding uh, levels of refinement in B and C. And some smoothing methods will be used in the regions of these meshes when the flow is happening from a coarser region to a finer region. Then only thing we should keep in mind is that, or we should have to check, is the transition regions, the geometry as well as the solution solving schemes should be uh, uh, should follow some smoother methods so that there should not be a abrupt jump in the results or in the methods. Next question. A hybrid mesh combines elements of both structured and unstructured grids. What is the potential benefit of using hybrid approach? Option A improves sorry. Option A improves accuracy everywhere in the domain. Option B simplifies mesh generation for complex geometries. Option C reduces computational cost significantly. Option D eliminates the need of mesh refinement. So the question is on hybrid mesh. You can inbox your answers. Yes, you are right. Option B, that is, simplifies the mesh generation for complex geometries. Again, in the previous example, as I said, uh, you can use some structured mesh here, whereas unstructured mesh here. So, uh, depending on the complexity of the parts or regions of a complex geometry, we can choose structured and unstructured grids for different regions of the same domain. So we have a large domain like the uh, manifold that's been discussed in our lecture videos. So we will be having a larger computational domain. Some part of it will be comparatively simpler or regular compared to some other portions. In such portions, we can use structured grids, and the portions which having highly irregular boundaries or uh, ellipsoid, circular, or such kind of shapes, then we can or some complex boundaries are there. There we can go for unstructured elements. So this by this using this method, it simplifies the mesh generation because if you are following either a structured or unstructured mesh for the entire geometry, it will uh, in, definitely increase the complexity of mesh generation. Next question is on Delaunay triangulation method. In Delaunay triangulation is a popular method for unstructured grid generation. It ensures that option A, all elements have same aspect ratio. Option B, no interior angle of the triangle exceeds a certain limit. Option C, the elements are distributed uniformly throughout the domain. Option D, the grid intensity is highest near boundaries. So the question is on Delaunay triangulation method. So which of the following is that the Delaunay triangulation method tried to ensure? Yes, option B is our answer. No interior angle of the triangle exceeds a certain limit. So it's somewhat simpler question because for a triangle, the first thing we can fix limits is for interior angles. Next, other method is to for area based thing, it can choose for circumradius. If you have a triangle and we are fitting a circle over it, then the center to that uh, the radius of that circle is called circumradius. So minimizing circumradius is another method, and we set limits for the interior angles of the triangles in Delaunay method, because if it's the interior angle, if it becomes ex excessively acute or obtuse, then uh, the skewness of the element will be affected, and which will result in poor results. Uh, okay, this we have already discussed in previous question, so we can just skip this question. Advancing friend method, uh, mesh generation involves have already been progressively adding elements from defined boundary. This we have already discussed. Next question: which unstructured mesh element type is best suited for 2D problems? Again, a simple question. The question is, which is the most preferred element type for 2D problems? Yes, option C is our answer. That is triangular. As we have already discussed, a triangle is the smallest or simplest, not smallest, the simplest shape which can represent an area. So, triangular triangulation of the surface is the uh, simplest and most used methods for unstructured or complex geometries. Unstructured grid generation or complex geometries. Next question. A good practice for unstructured grid generation in CFD includes option A, minimizing the number of elements for faster simulations. Option B, maintaining a uniform element size distribution throughout the domain. Option C, refining the mesh in regions with high gradients of flow variables. Option D, using the most complex element type of available for better accuracy. Similar question we have already discussed. You can run it quickly. Yes, option C. That is to refine mesh regions in high gradients of flow variables. So we can, in unstructured grids, we can choose to have finer mesh, and uh, other regions we can opt for coarser meshes. So uh, such mesh adaptation is the uh, primary property which we should aim in a unstructured mesh. Next question. Consider the numerical simulation solution of a wave equation using central difference scheme. Which of the following statements is true regarding its stability? So the question is on stability of the central difference scheme. Option A, it is always unstable regardless of the time step and spatial discretization. Option B, it is unconditionally stable for all time steps and mesh sizes. Option C, it is stable only for a specific time steps and mesh sizes satisfying a stability criterion. Option D, it is stable as long as the mesh size is sufficiently small. Yes, the answer is option C, that it is stable only for some time steps and mesh sizes which satisfy the stability criteria. Next question. When choosing a numerical scheme for a specific problem, it is crucial to consider option A, only the scheme's accuracy, option B, the problem's governing equations and desired properties, option C, computational efficiency solely, option D, the programming language used for implementation. So what should we consider while choosing a numerical scheme for a specific problem? Our answer is option B, problems governing equation and desired properties. So when we are choosing a numerical scheme, it should reflect or it should capture the governing equation, that's the partial differential equations. Whereas the computational efficiency mostly is taken care in the iterative methods. That's where when we are iterating the computational efficiency, mostly, and I'm not saying it is entirely there, it is mostly uh, taken care there. And scheme's accuracy is defined, not just the scheme accuracy, overall accuracy depends on the uh, entire method, not just numerical scheme. But the thing is, when we are solving for a flow problem or CFD, then the numerical scheme should capture our underlying physics. So that's for a specific problem. This it is not a general thing for any particular specific problem. That physical phenomenon driving that flow or something should be captured well by the numerical schemes. Next question is on von Neumann stability analysis. The von Neumann stability analysis analyzes the amplification factor of a numerical scheme. What does the amplification factor greater than 1 indicate? Simple question. You can answer quickly. Yes, you are right. Our amplification factor, so it is a ratio of error in n plus 1th step by error in nth step. So if it is greater than 1, that means it is the error is growing. So uh, it implies that the scheme amplifies the errors and it can become unstable. So there is nothing more. It should be more conclusive to say it will become unconclusive. So we can only say that it can become unstable. Our option is option C. So that's all for today's session. Thank you for joining. Yes. What are the type of career opportunities this week? Actually, CFD is again a broad field nowadays. Mostly, the first option you will get a CFD engineer is the first option. CFD engineer or CFD analyst in most of the flow-related problems. Most of the automotive, uh, uh, automotive companies as well as this pump turbine air conditioning, all such companies are recruiting CFD analysts or CFD engineers. Or if you are having some higher degrees in regarding CFD, you have maybe even hired as domain expert in fluid flow modeling and all. So it's a the thing is you should have to there are a lot of career opportunities, but you will have to CFD itself is a broad field nowadays, so you will have to pick some finer uh, areas of CFD. Is it for this chip cooling or electronic cooling or something, or you want to work in combustion, or itself CFD can be applied in a lot of fields. So even the uh, large buildings that like Burj Khalifa or something or such can for that itself we are doing CFD simulation, or weather forecast we are doing CFD simulation. So, you will be LB need some particular degree related to CFD along with this course, and also some uh, good portfolio that you have worked on some problems of, I already told some areas of your own liking in CFD, and you have worked out of these kind of problems with this much accuracy. And the thing is, you should be thorough with the basics of CFD. As you have understood from the course itself, it is just a set of tools and techniques. If you apply it wisely, then uh, any problems can be solved. So that uh, way of thinking should be developed. I think we can. I think that answers your question. Thank you.